Under the hood, training a digit classifier. Haven't seen what it looks like to train a variety of models in Chapter 2. Let's now look under the hood and see exactly what is going on. We'll start by using computer vision to introduce fundamental tools and concepts for deep learning. To be exact, we'll discuss the roles of arrays and tensors and of broadcasting, a powerful technique for using them expressively. We'll explain stochastic gradient descent, SGD, the mechanism for learning by updating weights automatically. We'll discuss the choice of a loss function for our basic classification task and the role of mini-batches. We'll also describe the math that a basic neural network is doing, and finally we'll put all of these pieces together. In future chapters, we'll do deep dives into other applications as well, and see how these concepts and tools generalize. But this chapter is about laying foundation stones. To be frank, that also makes this one of the hardest chapters because of how these concepts will all depend on each other. Like an arch, all the stones need to be in place for the structure to stay up. Also like an arch, once that happens, it's a powerful structure that can support other things. But it requires some patience to assemble. Let's begin. The first step is to consider how images are represented in a computer. Pixels, the foundations of computer vision. To understand what happens in a computer vision model, we first have to understand how computers handle images. We'll use one of the most famous datasets in computer vision, MNIST. And this is going to be the dataset that has those handwritten digits. It's a pretty famous dataset. Basically, for every single digit from 0 to 9, there's some number of variations of the way it's written, and the goal is to use these images and its labels. So for example, we have this one here, which is like number 2. This picture will be associated with the label 2, and during training, it's the job of the model is to try and match it up with the right label. So it's a classification task of these digits, and it'll be able to do some basic OCR on numbers in this case. For our experiments, we'll use one of the most famous datasets in computer vision, MNIST, for our experiments. MNIST contains images of handwritten digits collected by the National Institute of Standards and Technology and collated into a machine learning dataset by Jan LeCun and his colleagues. LeCun used MNIST in 1998 in LaNet 5, the first computer system to demonstrate practically useful recognition of handwritten digit sequences. This is one of the most important breakthroughs in the history of AI. Tenacity and deep learning. The story of deep learning is one of tenacity and grit by a handful of dedicated researchers. After early hopes and hype, neural networks went out of favor in the 1990s and 2000s, and just a handful of researchers kept trying to make them work well. 3 of them, Jan LeCun, Yoshua Bengio, and Geoffrey Hinton, were awarded the highest honor in computer science, the Turing Award, generally considered the Nobel Prize of Computer Science. In 2018, after triumphing despite the deep learning skepticism and disinterest of the wider machine learning and statistics community, Hinton has told of how academic papers showing dramatically better results than anything previously published would be rejected by top journals and conferences just because they used a neural network. LeCun's work on convolutional neural networks, which we will study in the next section, showed that these models could read handwritten text, something that had never been achieved before. However, his breakthrough was ignored by most researchers, even as it was used commercially to read 10% of the checks in the US. In addition to these 3 Turing Award winners, many other researchers have battled to get us where we are today. For instance, Jürgen Schmidhuber, who many believe should have shared who should have shared in the Turing Award, pioneered many important ideas, including working with his student Sepp Hochreiter on the long short-term memory LSTM architecture, widely used for speech recognition and other text modeling tasks and used in the IMDb example in Chapter 1. Perhaps most important of all, Paul Wermos in 1974 invented backpropagation for neural networks, the technique shown in this chapter and used universally for training neural networks. His development was almost entirely ignored for decades, but today it is considered the most important foundation of modern AI. There is a lesson here for all of us. On your deep learning journey, you will face many obstacles, both technical and even more difficult, posed by people around you who don't believe you'll be successful. There's one guaranteed way to fail, and that's to stop trying. We've seen that the only consistent trait among every fast AI student who's gone to be a world-class practitioner is that they are all very tenacious. For this initial tutorial, we are going to try and create a model that can classify any image as a 3 or 7. So let's download a sample of MNIST that contains images of just these digits. Okay, let's go and start up anti-gravity. And create a new chapter here. It'll be called Chapter 4, and we'll just name this book IPyNB. And then let's at least import some of the code that we were supposed to import. Maybe it's from here. Yep. Okay. So fast AI vision import all. How come I can't paste? Oh, it is plain text. Let's see. Make this as a code cell. Let's see here. You know what? Let's change this to Python. Oh, I don't have this yet. Let's see. Python. Restart extensions. Python. Come on. We have, oh, let's do Jupyter Notebook support. Maybe that's the reason why. Oh, geez. There we go. Okay, there we go. Looks better now. Okay, from fastai.vision import star. Okay, let's see if that works. All right, fast vision all import star. Oh, look, I have the autocomplete thing. That's super distracting. Let me just change that. Tab speed fast, snooze, advanced settings, editor, tab. There we go. Suggestions in editor, no tab to jump because it's annoying. Okay, so do we have a URL? We do have a URL. Okay, cool. So what are we supposed to do here? So path is going to be untar data urls.mnist sample. Easy enough. So we're going to download that untar data, so that I think automatically untars things. urls.mnist sample. There we go. Okay. So we're downloading the data set here. I'm not even sure. Is this like the number of bytes downloaded? Okay. So now we're done downloading that. Okay, we can see what's in this directory by using ls, a method added by fastai. This method returns an object of a special fastai class called L, which has all the same functionality of Python's built-in list, plus a lot more. One of its handy features is that when printed, It displays the count of items before listing the items themselves. If there are more than 10 items, it just shows the first few. Okay, let's try path.ls. Cool. So we have the labels, we have the train folder, and we also have the validation folder. So 3 items here. Not sure why this one has 9 items, but it's okay. The MNIST dataset follows a common layout for machine learning datasets, separate folders for the training set and validation set. Let's see what's inside the training set. So path, train, ls. Let's look at that. Path. Was it? Oh, parentheses. I didn't know you could do that. Path. Train. .ls. Okay. So it looks like we have digits for 7 and 3, which is what we're supposed to be doing here. Okay, so there's a folder of 3s and a folder of 7s. Okay, we've got that. In machine learning parlance, we say that 3 and 7 are labels or targets in this data set. Let's look in one of those folders using sorted to ensure we get the same order of files. So 3s and 7s, we're just going to ls and then do sorted, and then we're going to check out what's in 3s. Okay. So now path train 3.ls.sorted, and we can assign that to 3s. And why not just do 3s for now? Okay. So we have 6,131 examples of PNG files. And same for 7s. Path train 7.ls.sorted. 7s. So we have 6,265. Pretty balanced. As we might expect, it's full of image files. Let's take a look at one now. Here's an image of a handwritten number 3, taken from the famous MNIST dataset of handwritten numbers. Okay, IM3 path, 3's second element in the 3's array of paths. We're going to just call image open. We might have to import pillow, I guess, and then just display the image. Okay. So let's just import it up here. Or, yeah, let's just go in order. From PIL, is it PIL? Yeah, import image. Okay, so we'll import image. Then we're going to take the first path of 3, so IM path. So IM3 path is going to be 3's 1, so the second element. Then we are going to open, so IM3 is image.open, IM3 path, and we want to display IM3, and that displays the first image. So doing the same thing, IM7 path, 7's 1, IM7 is image.open, IM7 path, and then IM7. Okay, we have a 7 here, which looks like a 4. So I see we could probably confuse the CNN down the line. Okay, so here we are using the image class from the Python imaging library PIL, which is the most widely used Python package for opening, manipulating, and viewing images. Jupyter knows about PIL images, so it displays the image for us automatically. In a computer, everything is represented as a number. To view the numbers that make up this image, we have to convert it to a NumPy array or a PyTorch tensor. For instance, here's what the section of the image looks like converted to a NumPy array. So array So we're just going to use the array method or function, wrap it with that image, and then we can just display a slice of it. Okay, let's do that. So from actually, let's do this. Import numpy as MP. Okay, now we can then display mp.array im3, and then what was it again? 410 410 410 410. Cool. That looks about not the same. Okay, but I guess that's okay. D type UN8. I have like a different section. Well, actually, let's see. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 6. For me, I was. Oh, maybe it's this way around. So 0, 4, 3. Let's see here. Yeah, I don't know. Okay. I have no clue why that would be different. Wait. 3s. Yeah. Whatever. I'm still getting the array, so it could be from another example or another image. The 410 indicates we requested the rows from index 4 inclusive to 10 non-inclusive, and the same for the columns. NumPy indexes from top to bottom and from left to right. So this section is located near the top left corner of the image. Here's the same thing as a PyTorch tensor. Cool. So let's try that. Import torch as t. Okay, that might come back to haunt me. T.tensor. im3. Is it the same thing? Tensor. Okay. No, it doesn't work the same way. Oh. Oh, it's like this. Okay. Could not infer D type of PNG image file. Is it because I didn't do it correctly? Is it just, oh, it's from fastai. They probably do a lot of things underneath the hood. And maybe this is actually from fastai too. Let's see. There might be one from fastai. Probably not. It's okay. mp.array. Four ten 410. It's funny because this one looks closer. Actually, it is the same. Okay. We can slice the array to pick. Yeah, we can slice the array. Oh, okay. No, it's because I noticed. Yeah, I wrote it wrong. I did that. This will be better. I don't know what I'm doing. Okay, cool. I got the same thing now. Nice. Okay. We can slice the array to just pick part with the top of the digit in it, and then use a pandas data frame to color code the values using a gradient, which shows us clearly how the image is created from the pixel values. Oh, that's cool. So we create a tensor, a torch tensor from the image file. Then we pass in a portion of that to a pandas data frame, and then we can just set some fancy things to color the values with a specific intensity. Okay, so let's try that too. So im3 tensor is going to be tensor im3, and what was the range? 415 422. So 415 422. Next, we should probably try to import pandas. Import pandas as PD. There we go. Okay, and df equals pd.dataframe imt. Okay, im3t. So df equals pd.data frame im3t. After that, it's df.setStyleProperties, and then we just pass in this keyword args, I'm guessing. df.style.setProperties. Pass in, what's properties do we want? Set font size 6 point. Font size 6 point. Is that how we do it? It's like CSS, right? Then dot background gradient grays. Dot background gradient grays. Okay, let's see how that turns out. Very nice. Okay. You can see that the background white pixels are stored as a number 0, black is a number 255, and shades of gray are between the two. The entire image contains 28 pixels across and 28 pixels down, for a total of 768 pixels. This is much smaller than an image that you would get from a phone camera, which has millions of pixels, but it is a convenient size for our initial learning and experiments. We will build up to bigger full color images soon. So now you've seen what an image looks like to a computer. Let's recall our goal. Create a model that could recognize 3s and 7s. How might you go about getting a computer to do that? Stop and think. Before you read on, take a moment to think about how a computer might be able to recognize these two digits. What kinds of features might it be able to look at? How might it be able to identify these features? How could it combine them? Learning works best when you try to solve problems yourself rather than reading somebody else's answers. So step away from this book for a few minutes, grab a piece of paper and pen, and jot some ideas down. I'm guessing it's the location of the pixels and the values of them. More intense one means that it is part of that writing. That's my guess. And like eventually you learn that pattern in that region, and you learn that that thing is associated with the number 3 versus the number 7. Because I think this is just from like a CNN perspective. Like it's just scanning the regions of the picture in like square matrices, square regions. So here's the first idea. So this is the first try. Like what happens if we do pixel similarity? So here's a first try. How about we find the average pixel value for every pixel of the 3s and then do the same for the 7s. This will give us two group averages, defining what we might call the ideal 3 and 7. Then to classify an image as one digit or the other, we see which of these two ideal digits the image is most similar to. This certainly seems like it should be better than nothing, so it will make a good baseline. Jargon, baseline. A simple model that you are confident should perform reasonably well. So that's baseline. It should be simple to implement and easy to test so that you can test each of your improved ideas and make sure they are always better than your baseline. Without starting with a sensible baseline, it is difficult to know whether your super fancy models are any good. One good approach is to create a baseline is doing what we have done here. Think of a simple, easy to implement model. Another good approach is to search around to find other people who have solved problems similar to yours and download and run their code on your dataset. Ideally, try both of these. So step 1 for our simple model is to get the average of pixel values for each of our two groups. In the process of doing this, we'll learn a lot of neat Python numeric programming tricks. Let's create a tensor containing all of our 3s stacked together. We already know how to create a tensor containing a single image. To create a tensor containing all the images in the directory, we will first use a Python list comprehension to create a plain list of the single image vectors. So remember, we're just trying out an option, a solution option here, not necessarily the solution. So we're going to open every single image in the 7s and 3s path lists, and we're going to convert them to a tensor after we have opened them. And 7 tensors and 3 tensors should all be torch tensors. I think we can do that. So 3 tensors. That would be, in this case, image.open im path, and let's just say tensor im path for im path in 3s. Same thing, 7 tensors, tensor image dot open, that'll be im path for im path in 7s. Okay, so let's create those, and then let's find the length of both of them. So len 3 tensors and then len 7 tensors. And we've done that successfully. Great. List comprehensions. List and dictionary comprehensions are a wonderful feature of Python. Many Python programmers use them every day, including the authors of this book. They are part of the idiomatic Python, but programmers coming from other languages may have never seen them before. A lot of great tutorials are just a web search away, so we won't spend a long time discussing them now. Here is a quick explanation and example to get you started. A list comprehension looks like this. New list is going to be this wrapped around, but basically you're going to iterate through your list with some condition. This is optional actually. And then you're going to do something with that element that is here, defined here. So it's a shorthand way to iterate through a list up to a certain point, or all the entire list, and then operate and put it into a new array, kind of like a map. So this will return every element of a list that is greater than 0. Oh, so not a stopping point. It's that's if, well, I guess a filter. There are 3 parts here: the collection you are iterating over, a list, and an optional filter. Yeah, it is optional, and something to do with each element. So this is kind of like a map. It's not only shorter to write, but also way faster than the alternative ways of creating the same list with a loop. We'll also check that one of the images looks okay, since we now have tensors which Jupyter by default will print as values, rather than PIL images, which Jupyter by default will display images. We need to use FastAI's show image function to display it. So this show image from FastAI most likely knows how to take in a tensor and turn it back into an image. So let's try it out. So show image, 3 tensors. Let's just start at 1. That's pretty cool. Yeah, it's in color though. Would that be okay? Let's see. Guess that'll be okay. Okay, so yeah, it's this is supposed to be black, but it's purple, and this is supposed to be white, but it's yellow. For every pixel position, we want to compute the average over all the images of the intensity of that pixel. To do this, we first combine all the images in this list into a single 3-dimensional tensor. The most common way to describe such a tensor is to call it a rank 3 tensor. We often need to stack up individual tensors in a collection into a single tensor. Unsurprisingly, PyTorch comes with a function called stack that we can use for this purpose. Some operations in PyTorch, such as taking a mean, require us to cast our integer floats or integer types to float types. Since we will be needing this later, we'll also cast our stack tensors to float now. Okay, so we're going to go through every single one of the tensors and just turn them into floats because they are integers at the moment. Each pixel value is represented from 0 to 255. Casting in PyTorch is as simple as writing the name of the type you wish to cast to and treating it as a method. Generally, when images are floats, the pixel values are expected to be between 0 and 1. So we'll also divide by 255 here. So torch.stack is going to receive the entire list of tensors, and .float is going to convert every single one of these to be a floating point type of tensors. And we need to divide it by 255 to normalize the pixel values to be between 0 and 1. So stacked 7s and stacked 3s. Let's see if I can remember how to do this. So stacked 3s is going to be torch dot stack, and that's going to take in our 3's tensors. 3's. We should probably call it 7. No, we'll just name it like that. Okay. And then we're going to cast all of them to float, and then we'll divide them by 255. And we could do the same thing with stacked 7s. Torch.stack 7 tensors. Oh, what did I just do? Control Z. Okay, 7 tensors. Float 255. And we also want to display stacked 3's dot shape, I think, and then stacked 7's dot shape. Okay, so 6,131 28 by 28, then 6,265 of 28 by 28 tensors. Perhaps the most important attribute of a tensor is its shape. This tells you the length of each axis. In this case, we can see that we have 6,131 images, each a size 28 by 28 pixels. There's nothing specifically about this tensor that says that the first axis is the number of images, the second is the height, and the third is the width. The semantics of a tensor are entirely up to us and how we construct it. As far as PyTorch is concerned, it's just a bunch of numbers in memory. So we have to interpret what each dimension represents. The PyTorch is just numbers. The length of a tensor's shape is its rank. So len of stack 3's, we take that shape, and that's the rank. It's really important for you to commit to memory and practice these bits of tensor jargon. Rank is the number of axes or dimensions in a tensor. Shape is the size of each axis of a tensor. So rank is just how many D's your tensor is, and then shape is okay how in each dimension, how long is it? Alexis says, watch out because the term dimension is sometimes used in two ways. Consider that we live in three-dimensional space, where a physical position can be described by a vector v of length 3. But according to PyTorch, the attribute v.ndim, which sure looks like the number of dimensions of v equals to 1, not 3. Why? Because v is a vector, which is a tensor of rank 1, meaning that it only has one axis, even if that axis had a length of 3. In other words, sometimes dimension is used for the size of an axis. Space is three-dimensional. While other times it is used for the rank or the number of axes. A matrix has two dimensions. When confused, I find it helpful to translate all statements into terms of rank, axis, and length, which are unambiguous terms. We can also get a tensor's rank directly with ndim, stack 3's ndim, 3. Okay. Finally, we can compute what the ideal 3 looks like. We calculate the mean of all the image tensors by taking the mean along dimension 0 of our stacked rank 3 tensor. This is the dimension that indexes over all the images. In other words, for every pixel position, this will compute the average of that pixel all over the images. The result will be one value for every pixel position, or a single image. So mean 3, the average 3 is going to take the stacked 3's, find the mean across dimension 0. So each one of the 28 by 28s, and then we're going to show the ideal 3. Let's try that. So mean 3, and what's that? Stack 3's dot mean, okay, at dimension 0. Stack 3's dot mean 0. and then we're going to then turn it into an image. Yeah, show image mean 3. Show image mean 3. Okay, that's blurry as expected because it's averaging. So we can also do mean 7. Stacked 7's dot mean 0. Show image mean 7. That's your average 7. According to this data set, this is the ideal number 3. You may not like it, but this is what peak number 3 performance looks like. That's how you draw the best 3. You can see how it's very dark where all the images agree. It should be dark, but it becomes wispy and blurry where the images disagree. Let's do the same thing for the 7s, but put all the steps together at once to save time. Now, let's now pick an arbitrary 3 and measure its distance from our ideal digits. Stop and think. How would you calculate how similar a particular image is to each of our ideal digits? Remember to step away from this book and jot down some ideas before you move on. Research shows that recall and understanding improves dramatically when you are engaged with the learning process by solving problems, experimenting, and trying ideas yourself. I don't know, maybe compare pixel by pixels, see if they match up, or do what are those like distance formulas things, or maybe like a pixel form of Levenstein. Let's see. So here's a sample 3. Okay, we'll just do A3. A3 is going to be one of those stacked 3s. 1, show image. A3. Okay, very clear and crisp. How can we determine its distance from our ideal 3? We can't just add up the differences between the pixels of this image and the ideal digit. Some differences will be positive while some will be negative, and these differences will cancel out, resulting in a situation where an image that is too dark in some places and too light in others might be shown as having 0 total differences from the ideal. That would be misleading. To avoid this, data scientists use 2 main ways to measure distance in this context. Take the mean of the absolute value of differences. Okay, so that's like a score. So are you taking like basically every single pixel and just seeing what the difference is for the pixel values and then add them all up and then average it? The absolute value is the function that replaces negative values for positive values. This is called the mean absolute difference, or L1 norm. Take the mean of the square of differences, which makes everything positive, and then take the square root, which undoes the squaring. This is called root mean squared error, so RMSE or L2 norm. Oh, I've heard of these, but I've forgotten. So it's okay to have forgotten your math. In this book, we generally assume that you have completed high school math and remember at least some of it, but everybody forgets some things. It all depends on what you happen to have had reason to practice in the meantime. Perhaps you have forgotten what a square root is or exactly how they work. No problem. Anytime you come across a math concept that is not explained fully in this book, don't just keep moving on. Instead, stop and look it up. Make sure you understand the basic idea, how it works, and why we might be using it. One of the best places to refresh your understanding is Khan Academy. For instance, Khan Academy has a great introduction to square roots. How about, let's just ask Mr. GPT. So let's see. What does the mean absolute difference L1 norm tells us? What is the root mean squared error or L2 norm tell us? Okay, let's start a new one. So what does the mean absolute difference L1 norm tell us between 2 matrices, and what does the root mean squared error or RMSE L2 norm tell us? I am not very good at math. Would appreciate a good explanation. Okay. Wow, we should have thought, but that was really fast. Okay, so think of each matrix as just a big list of numbers arranged in a grid. Comparing two matrices usually means how different are the numbers in the same positions. Let A and B be two matrices of the same shape. Define the error matrix. Okay, so basically this contains all the differences between A and B. So each entry E sub ij is going to be the difference between an individual element in A sub ij minus B sub ij. So that's how far off they are from each other. So with the absolute difference, you're just taking the absolute value here and you're summing it all up, and then you're just averaging them. Okay, that makes more sense now. So go through every single pixel, just take for each pixel, just take the difference, absolute value, add it to a running sum, and just divide it by the total number of pixels. Okay, what that tells us though is, in plain English, on average, how many units apart are these matrices per cell? On average, how many units apart are these matrices per cell? If MAE equals 0, they're identical. If MAE equals 2, then typical entries differ by about 2. So ideally, we want it to be less than, very close to 0. Okay, so the L1 norm connection. The L1 norm of the error, sometimes written in, I guess, I don't know what this is called, loosely, is basically the sum of absolute errors. If you divide that by n, you get the mean absolute difference. So the key behavior is it treats all errors linearly. Being off by 10 counts exactly twice as much as being off by 5. It's less sensitive to big outliers than RMSE. Okay, so if the mean absolute difference, okay, if it's 2, then for every entry, they differ by about 2. Okay, sure, like maybe two intensity levels in this case. RMSE, root mean squared error, related to L2. What you do is you take a difference in each pixel, you square it, so you square it, okay, so you square that value, that would be positive, I guess, and then average out the squared values. But we're taking the sum first, and then we average the square values, and then take the square root to return the original units. So what does this tell us? A typical error size, but with extra punishment for big mistakes. So RMSE 0 means identical. RMSE has the same units as your matrix values because of the square root. The L2 norm connection, L2 norm of the error vector is this. So without the averaging out. So L2, L1 is just basically the same of the corresponding ones, but not dividing by the total number. Okay. RMSE is basically that, but normalized by n, mean first. So it becomes, oh, that's why it's called mean. It becomes an average per entry style number. Key behavior penalizes big errors more. An error of 10 contributes to 10 to 2, which means 100, while 5 contributes to 25. So 10 is 4x worse than 5. If you care a lot about large deviations, RMSE is useful. Okay, so one is linear and one would be like kind of more, I don't know what you call it, like curvy. It's not entirely exponential, it's not quadratic. Or is it quadratic, right? It is quadratic. There we go. A tiny example. So we have error in 4 cells, 0, 0, 0, 1, 10. Mean absolute error is going to be 2.5. So each will differ about 2.5, which is really hard to tell because now these, like, yeah, I see. RMSE is going to be 5. So you're using the same data, but RMSE is bigger because it yells that 10 is a big deal. So the RMSE will just tell us that, hey, like, you have some values in here. Not exactly sure what values, but go check it out. Like, there's something there that is causing everything to be thrown off. So when to use which? Use MAE, mean absolute difference. when you want a straightforward average error that isn't dominated by a few large mistakes. Use RMSE2 when large errors, or RMSE-L2 when large errors are especially bad and you want your metric to reflect that strongly. So intuition is use L1 MAE, average distance per cell, RMSE, average distance per cell, but big mistakes count a lot more. Yeah. Yes, they represent images. Just working through fast.ai book on chapter 4 about MNIST digit classification. It'll be pretty funny if it understood all that. Okay. Oh, got it. The matrices are image and pixel value. Assuming image. Okay, whatever. That's not what we're looking for. Okay. So let's try both of these now. We're going to take the absolute mean of the difference between every single pixel in one of our given 3 samples, along with every one of the pixels between our mean 3. Take the absolute value and just take the mean of each. Then we also have the square root version, and then we can just see what they are. So looks like they don't differ by too much here. Okay, let's do that. So dist 3 ABS. So that's going to be what? A3 minus mean 3 dot ABS. Is that how it works? And then dot what? So yeah, it's absolute difference, right? And do we just average it? Yeah, we average it. So mean, and then we also have this 3 square. So it's A3 minus mean 3 dot square, or just do that. So it's kind of just probably square every single element. And then what do we do here? Do we take the mean and then we square root that? Yeah, we take the mean and then we square root that. So we take the mean and then we square root that. I should probably wrap this in quotes too. So let's just do that again just to make sure. So you take the mean and then you square root that. Okay. And then dist 3 ABS, dist 3 square root, or square. Okay, so we got the same answer. So we'll do that same with dist 7 ABS. Shoot, did we even do? Okay, let's add in A7. A7 is going to be stacked 7s 1 show image A7. Is that right? Yes. Okay, let's do that. A7 minus mean 7 dot ABS dot mean dist 7 square is going to be A7 minus mean 7 dot ABS square dot not ABS dot mean dot square root. Okay, then we return dist 7 ABS, then dist 7 square. Okay, 1304, 2585. Uh-oh. A3 means 7. Oh, okay. They did that on purpose. Oh, whew. Okay. So let's just do that again, just to mess around. So okay, what does a 3? How much does a 3 differ from a 7? I see what they're trying to do. That's how you distinguish between 3 and a 7. If you have like a high error, between your 3 versus your average 7, then yeah, for sure it's a 3. So it's like a 1 or the other. But then you would have to know what your, like, yeah, in this case you have to know what your average error is for this specific 3 against your mean 3. So let's try that actually. You know what, we don't need this. Let's just do it this way because that does tell us something. Yeah, 0.3021, 0.1586 is high, but it's not like magnitudes different, so it's kind of hard to tell. In both cases, the distance between our 3 and the ideal 3 is less than the distance to the ideal 7, so our simple model will give the right prediction in this case. PyTorch already provides both of these as loss functions. You'll find these inside torch and functional, which PyTorch team recommends importing as f and is available by default under that name in fastai. So f.l1 loss is going to be turning your a3 float with mean 7. Okay, same. MSE loss. Okay, so here MSE stands for mean squared error, and L1 refers to standard mathematical jargon for mean absolute value. In math, it's called the L1 norm. Sovin says, intuitively, the difference between L1 norm and mean squared error is that the latter will penalize bigger mistakes and more heavily than the former. Oh, we read that from GPT. And be more lenient with small mistakes. Jeremy says, when I first came across this L1 thingy, I looked it up to see what on earth it meant. I found on Google that it is a vector norm using absolute value, so I looked up vector norm and started reading. Given a vector space V over a field F of the real or complex numbers, a norm on V is a non-negative valued any function P where V, I guess V, is projected on a space of 0 to positive infinity, so positive, right? A positive vector with the following properties. For all elements within the field and all of elements, I guess UV in the vector is any dimensions, I guess. P U plus V is going to be less than, okay, I don't get this. Then I stopped reading. I'll never understand math. I thought for the 1000th time. Since then, I've learned that every time these complex mathy bits of jargon come up in practice, it turns out I can replace them with a tiny bit of code. Like the L1 loss is just equals to a minus b dot abs dot mean, where a and b are tensors, and I guess mathy folks just think differently than I do. I'll make sure in this book that every time some mathy jargon comes up, I'll give you a little bit of code it's equal to as well, and explain in common sense terms what is going on. Okay. So we just completed various mathematical operations on PyTorch tensors. If you've done numeric programming in PyTorch before, you may recognize these as being similar to NumPy arrays. Let's have a look at those two important data structures. NumPy arrays and PyTorch tensors. NumPy is one of the most widely used library for scientific and numeric programming in Python. It provides similar functionality and a similar API to that provided by PyTorch. However, it does not support using the GPU or calculating gradients, which are both critical for deep learning. Therefore, in this book, we will generally use PyTorch tensors instead of NumPy arrays where possible. Note that fastai adds some features to NumPy and PyTorch to make them a bit more similar to each other. So wrappers, a lot of wrappers. If any code in this book doesn't work on your computer, it's possible that you forgot to include a line like this at the start of your notebook from fastai.vision.all import stars. So that was what we were having trouble with earlier. But what are arrays and tensors, and why should you care? Python is slow compared to many languages. Anything fast in Python, NumPy, or PyTorch is likely to be a wrapper for a compiled object written and optimized in another language, specifically C. In fact, NumPy arrays and PyTorch tensors can finish computations many thousands of times faster than using pure Python. A NumPy array is a multi-dimensional table of data with all items of the same type. Since that can be any type at all, they can even be arrays of arrays, with the innermost arrays potentially being different sizes. This is called a jagged array. By multi-dimensional table, we mean, for instance, a list with a dimension of 1, a table or a matrix dimension of 2, a table of tables or a cube dimension of 3, and so forth. If the items are all of simple type, such as integer or float, NumPy will store them as a compact C data structure in memory. This is where NumPy shines. NumPy has a wide variety of operators and methods that can run computations on these compact structures at the same speed as optimized C because they are written in optimized C. A PyTorch tensor is nearly the same thing as a NumPy array, but with an additional restriction that unlocks additional capabilities. It's the same in that 2 is a multi-dimensional table of data with all items of the same type. However, the restriction is that a tensor cannot use just any old type. It has to use a single basic numeric type for all components. As a result, a tensor is not as flexible as a genuine array of arrays. For example, a PyTorch tensor cannot be jagged. That's the difference. How should I do this? So jagged array is something like this, where let's say you have an array and you have an array of arrays. Something like this is actually considered jagged because each element can be of a different length in this case. That is what NumPy allows versus Torch. Torch really needs to have all the elements be aligned with each other for it to be considered a proper tensor in this case. So this is jagged, this is not jagged. Jagged means you have each element of an array of arrays be of some different length, and this is not jagged. Okay. It is always a regularly shaped multi-dimensional rectangular structure. The vast majority of methods and operators supported by NumPy on these structures are also supported by PyTorch, but PyTorch tensors have additional capabilities. One major capability is that these structures can live on the GPU. So PyTorch can actually have the tensors be put into GPU memory. That's what living on the GPU means. In which case, their computation will be optimized for the GPU and can run much faster, given lots of values to work on. In addition, PyTorch can automatically calculate derivatives of these operations, including combinations of operations. As you'll see, it would be impossible to do deep learning in practice without this capability. So Vince says, if you don't know what C is, don't worry, you won't need it at all. In a nutshell, it's a low level. Low level means more similar to the language that computers use internally. Language that is very fast compared to Python. To take advantage of its speed while programming in Python, try to avoid as much as possible writing loops and replace them by commands that work directly on arrays or tensors. I do disagree that C is low level. It's not really low level. I still think it's a high level language. Perhaps the most important new coding skill for a Python programmer to learn is how effectively to use array or tensor APIs. We will be showing lots more tricks later in this book, but here's a summary of the key things you need to know for now. So to create an array or tensor, pass a list or list of lists or list of lists of lists, etc. to the array or tensor. So create this as a normal Python list first. Then you can either create a NumPy array or a PyTorch tensor. So this one R is NumPy, this one is PyTorch. All of the operations that follow are shown on tensors, but the syntax and results for NumPy arrays are identical. You can select a row. Note that like lists in Python, tensors are zero indexed, so one refers to the second row or column. Or a column by using colon to indicate all of the first axis. We sometimes refer to the dimensions of tensors as axes. So take everything in the first axis and then go up to what, like the first element or second element. So in this case, all of the first, I think it works. Oh, does it work through vertically? Okay. You can combine these with Python slice syntax. Start n with n being excluded to select part of a row or column. So take the first one here, and then what do? We go from what, 1 to 3. What does that mean? So the second element here. Wait a second. Why is this one tensor 2 5 when I can just select all of the first axes? And this one is also selecting what, the second axis? Okay. Huh. Sure. And then we go from 1 to 3. So that's confusing, right? Like, so we select the first one, we go from 1 to 3. Yeah, I don't know. I can't visualize this just by reading. Okay, whatever. You can combine these with Python slice syntax with n being excluded to select part of a row or column. And you can use the standard operators such as plus, minus, multiply, and divide. So tensor plus 1 should add 1 to every single element. Tensors have a type. Tensor.type is torch long tensor, and we'll automatically change that type as needed. For example, from int to float. So we change it from, from int to float by multiplying by 1.5. Everything in here also changes into a float. So is our baseline model any good? To quantify this, we must define a metric. Computing metrics using broadcasting. Recall that a metric is a number that is calculated based on the predictions of our model and the correct labels in our data set. In order to tell us how good our model is, for instance, we could use either of the functions we saw in the previous section, mean squared error or mean absolute error, and take the average of them over the whole data set. However, neither of these are numbers that are very understandable to most people. In practice, we normally use accuracy as the metric for classification models. As we've discussed, we want to calculate our metric over a validation set. This is so that we don't inadvertently overfit. That is, train a model to work well only on our training data. This is not really a risk with the pixel similarity model we're using here as a first try, since it has no trained components. But we'll use a validation set anyway to follow normal practices and to be ready for our second try later. To get a validation set, we need to remove some of the data from training entirely so that it is not seen by the model at all. As it turns out, the creators of the MNIST dataset have already done this for us. Do you remember how there was a whole separate directory called valid? That is what this directory is for. So to start, let's create tensors for our 3s and 7s from that directory. These are the tensors we will use to calculate a metric measuring the quality of our first try model, which measures distance from an ideal image. Okay, so we're going to combine all the images in the directory where all the 3's images are at. So by doing ls, we get all the paths. So for every single path here, we're going to open and turn it into an image and then convert that to a tensor. And then torch.stack will then create a multi-dimensional tensor. So like a list of all these images in the valid 3 tensors. So validation data set. So we'll do that for 3 and 7, and then we're going to normalize both of them. Okay, let's see if I can remember this. Alrighty. So first things first, valid 3 tens. So we're going to create a tensor off from an image, and the image is O. So for O in path, what is it? Path slash valid slash 3. Is that what it was? Dot ls. Was that it? And then what is it for? And I think it has to be an array, right? So okay. Tensor. Yeah, so tensor. Oh, we have to create the array of tensors, not just individual tensors. And then we torch.stack. Okay. Close enough. Okay. So an array of tensors, not an array image. I would assume that we can also create a big tensor off from an array, but that's okay. And torch.stack. So all of these guys here. And then let's just normalize them. I think it's just as simple as dividing by 255.0. And let's see what the shape of this is afterwards. Okay, so we already have issues. What's the issue? Cannot convert np.nd array of type numpy object. The only supported types are float 64, float 32, float 16. Okay, so on. Why? What did we do? Torch.stack, tensor image open. That looks okay. Path valid 3. So torch.stack, tensor image. Oh, I put 0. That's the reason why. Okay. Let's see. For O in path. Come on. Image open. This one. There we go. Parentheses fighting. There we go. Okay. This is parentheses. Okay, so now we have our validation set. It's going to be 1010 images of 28 by 28 images. And I think that's what he got too. Yep. And then we'll do the same thing for the 7 tensors. It's the same thing again. Valid 7 tens. Torch.stack. Tensor image open. So take every single path. Typo. I need to get a real keyboard soon. For each path in the paths found in the validation directory for the 7 images, we do that by calling ls. Then what we want to do is go through every tensor and normalize it to be somewhere between 0 and 1 by dividing by 255.0, because that's the max for integer 8 pixel value. Okay, valid 7 tens dot shape. Okay, cool. 1028, 28 by 28. Okay, so we have these two tensors all ready to go now. It's good to get in the habit of checking shapes as you go. Here we see 2 tensors, one representing the 3's validation set of 1010 images of size 28 by 28, and one representing the 7's validation set of 1028 images of size 28 by 28. We ultimately want to write a function is3 that will decide whether an arbitrary image is a 3 or a 7. It will do this by deciding which one of our 2 ideal digits that arbitrary image is closer to. For that, we need to define a notion of distance that is a function that calculates the distance between 2 images. We can write a simple function that calculates the mean absolute error using an expression very similar to the one we wrote in the last section. So mnist distance is going to be image 1, image 2. We're going to return, I think this is just a simple, yeah, is this the mean, root mean? No, this is the absolute mean. Yeah, this is the absolute mean. Okay, absolute mean error. But what is -1, -2 mean? Is that, I don't know what that means. Okay, well, let's just write that. So return this, and then we're going to call mnist distance with one of the examples that we have, and then our ideal 3, and that will give us this value here. Okay, let's just write the mnist distance. It's just a wrapper, but I just don't know what this means. It's okay, let's just figure it out. Def mnist distance AB will return A minus B dot what was it, mean, or .ibs dot mean, and then I don't know what this means. Okay, and mnist distance, we had a 3, and then we also had, what was it called, mean 3. Okay, I hope he explains what -1, -2 is. Okay, so this is the same value we previously calculated for the distance between these two images, the ideal 3, mean 3, and the arbitrary sample 3, A3, which are both single image tensors with the shape of with 28 and 28. Maybe, maybe take the last like dimension, like these are probably the dimensions maybe. But to calculate a metric for overall accuracy, we'll need to calculate the distance to the ideal 3 for every image in the validation set. How do we do that calculation? We could write a loop over all of the single image tensors that are stacked within our validation set tensor. Valid 3/10, which has a shape of 1010, 28, 28, representing 1010 images. But there's a better way. Something interesting happens when we take this exact same distance function designed for comparing two single images, but pass it as an argument to valid 3/10, the tensor that represents the 3's validation set. Okay, so mnist distance is going to be, so you have the single mean 3, but then you have all of the validations here. You get back a bunch of tensors. Okay. And for every individual one of these values, they are the error, the mean absolute error between that element inside valid 3/10 against the ideal 3, the mean 3. So instead of complaining about shapes not matching, it returns a distance for every single image as a vector, a rank 1 tensor of length 1010, the number of 3's in our validation set. How did that happen? So take another look at our function mnist distance, and you'll see what we have there. The subtraction a minus b. The magic trick is that PyTorch, when it tries to perform a simple subtraction operations between two tensors of different ranks, they will use broadcasting. It will automatically expand the tensor with the smaller rank to have the same size as the one with the larger rank. Broadcasting is an important capability that makes tensor code much easier to write. Okay, so you want to take the mean of the last dimension maybe, and then the other, like the last two. Okay, so after broadcasting, you know what, let's just do this. What does this mean here? What does this mean? Just copy, let's see. Okay. Working through Fast AI book, chapter 4, mnist data. I see this code. What does the -1, -2 mean here? Let's see. Okay. In PyTorch and NumPy, a tensor has dimensions. You can refer to dimensions by index. This is what I've been trying to articulate. -1 is the last dimension. -2 is the second to last dimension. So assuming these are all tensors of 3 dimensions, we're going to take the last dimension, taking the mean, last dimension, and then second to last dimension. So take the mean over the last 2 dimensions. For MNIST images, tensors are typically shaped like either a single image, batch of images, okay? If it's a batch like this, then -1, -2 refers to 28, 28, average over height width, leaving you with 1 distance per image. Okay, that's why it works for computing average pixel difference. Okay, so does that mean we could have passed in something like how should we say this, dot mean 28, 28? I don't know. It takes dimension in this is axis to reduce over. Oh, okay. Oh, this is okay. Cool. So okay. So we know that the 28s are over here. We can just use it this way. Okay. This is just me being silly. All right. Okay. So this works because if earlier dimensions change, like we add another dimension, another batch of batches, for example, we'll still have consistency. So, yeah. Okay, that makes more sense. Okay, cool. So let's do this over our entire set of tensors. So valid 3 dist is going to be MNIST distance over the valid 3 tens, and then the mean 3, and then we can check that out through that. So that makes sense. We might as well do that for the 7 too. And this distance valid 7 tenths, and I think we want to check mean 3, right? Because that's, we want to compare the distances. So how far is a 7 between your average 3? So definitely on average is higher. So you look at these numbers here. So these 7s are obviously not close to a 3. So instead of complaining about shapes not matching, it returned the distance for every single image as a vector, rank -1 tensor of length 10, 10, the number of 3s in our validation set. How did that happen? Take another look at our function MNIST distance, and you'll see we have there the subtraction a minus b. The magic trick is that PyTorch, when it tries to perform a simple subtraction operations between 2 tensors of different ranks, we will use broadcasting. It will automatically expand a tensor with a smaller rank to have the same size as the one with the larger rank. Okay, so it is actually this mean 3 here, this single tensor here will be repeated over to match this one here. Okay. Broadcasting is an important capability that makes tensor code much easier to write. After broadcasting, so the 2 argument tensors have the same rank, PyTorch applies its usual logic for 2 tensors of the same rank. It performs the operation on each corresponding element of the 2 tensors and returns the tensor result. For instance, 123 plus 111 is 234. So in this case, PyTorch treats mean 3, a rank 2 tensor representing a single image, as if it were 1010 copies of the same image, and then subtracts each of those copies from each 3 in our validation set. What shape would you expect this tensor to have? Try to figure it out yourself before you look at the answer here. So it's probably going to be the same thing. Okay. We are calculating the difference between our ideal 3 and each of the 1010 3s in the validation set. So for each 28 by 28 images, resulting in the shape of 1010, 28, 28. Okay, yeah, because we're subtracting the individual values, individual pixel values, and these two are the same in terms of like being 28 by 28 images anyway. So there are a couple of important points about how broadcasting is implemented, which make it valuable not just for expressivity, but also for performance. So PyTorch doesn't actually copy mean3 10 times, 1010 times. It pretends it were a tensor of that shape, but doesn't allocate any additional memory. It does the whole calculation in C, or if you're using a GPU, in CUDA, the equivalent of C on the GPU. Tens of thousands of times faster than pure Python, up to millions of times faster on a GPU. This is true of all broadcasting and element-wise operations and functions done in PyTorch. It's the most important technique for you to know to create efficient PyTorch code. Next, in MNIST distance, we see ABS. You might be able to guess now what this does when applied to a tensor. It applies the method to each individual element in the tensor and returns a tensor of the results. That is, it applies the method element-wise. So in this case, we'll get back 1010 absolute values. Finally, okay, here's the one I was confused about. Finally, our function calls mean over the tuple of -1, -2. The tuple -1, -2 represents a range of axes. In Python, -1 refers to the last element and -2 refers to second to last. So in this case, this tells PyTorch that we want to take the mean ranging over the values indexed by the last two axes in the tensor. The last two axes are the horizontal and vertical dimensions of an image. After taking the mean over the last two axes, we are left just with the first tensor axis, which index over our images, which is why our final size was 1010. In other words, for every image, we average the intensity of all the pixels in that image. We'll be learning lots more about broadcasting throughout this book, especially in chapter 17, and we'll be practicing it regularly too. We can use MNIST distance to figure out whether an image is a 3 by using the following logic. If the distance between the digit in question and the ideal 3 is less than the distance to the ideal 7, then it's a 3. If the distance between the digit in question, so anything from the validation set, and the ideal 3 is less than the distance to the ideal. Oh, okay. Yeah, of course, because the closer it is to ideal 7, the evidence is closer to being a 7. Okay, then it's a 3. This function will automatically do broadcasting and be applied element-wise, just like all PyTorch functions and operations. Okay, so we have a mean 3 and mean 7, so it is a 3. Okay, so then we'll return MNIST distance x and then mean 3. If that is less than the one with mean 7, then obviously it's a 3. Well, not obviously, but we could conclude. So def is 3x. We want to return the Boolean. Basically, if the MNIST distance of x is of mean 3 is less than MNIST distance of x and mean 7, then that means it is a 3. Okay, let's just define that function now. So let's test it in our example case. So is 3 with a 3 and then is 3 a 3.float turns that result into a tensor. Okay, is 3 a 3 and then is 3 a 3.float. Okay, that's true. Note that when we convert the Boolean response to a float, we get 1.0 for true and 0.0 for false. Thanks to broadcasting, we can also test it on the full validation set of 3s. So that should all be true, 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 true. Now we can calculate the accuracy for each of the 3s and 7s by taking the average of the function for all 3s and its inverse for all 7s. Okay, so we want to check to see if all the valid 7 tensors are 3s, so accuracy of it being 7 is just the inverse. Okay, so to find the accuracy of 3, we want to broadcast. So accuracy 3 is going to be is 3 over the vector, not vector, what is it, valid 3 tens, right? Okay, so that's going to be all of the accuracies. And then did we do dot float? Right, that's what we did, right? Or yeah, dot float. So that's individual accuracies, but we want to know the mean. Okay. By taking the average of that function for all threes and inverse for sevens. Okay, so oh yeah, you're trying to calculate the percentage accuracy. Okay, so dot mean. Then you have accuracy 7, and that's just inverse. So 1 minus is 3, and I believe that's valid 7/10. Dot float, is it outright? Yeah, dot float dot mean. So we turn these to dot float, then we inverse, then we'll get the mean. Okay, so dot float dot mean, and then we can say that's equal accuracy 3, accuracy 7. Run that, 91 and 98. That is not bad at all. Yeah. Okay, so this looks like a pretty good start. We're getting over 90% accuracy on both 3s and 7s, and we've seen how to define a metric conveniently using broadcasting. But let's be honest, 3s and 7s are very different looking digits, and we're classifying only 2 out of the possible 10 digits so far. So we're going to need to do better. To do better, perhaps it is time to try a system that does some real learning, one that can automatically modify itself to improve its performance. In other words, it's time to talk about the training process and SGD.